Okay, question 12. Final question. Quite a big one. Okay, so in an experiment, 500 fruit flies were released into a controlled environment. After 10 days, 650 fruit flies were present. Munira believes that n, the number of fruit flies present at time t days after the fruit flies are released, will increase at the rate of 4.4% per day. She proposes that the situation is modelled by n equals a k to the t. Part 1 wants us to write down the values of a and k. Okay, so we know then when t is 0, n is 500. Now our model is n is a k to the t. So we're going to get 500 is a k to the 0, which means a is 500. Now k is going to be our decimal multiplier. So 4.4% is 0.044. So k is 1.044. So n is 500 times 1.044 to the power t. Cool. Part 2 wants us to determine whether the model is consistent with the value of n when t is equal to 10. So, we know when t is equal to 10, n is 650. So, when t is 10, n should be 650. Now, by the model, we get n is 500 times 1.044 to the power 10. Now this gives us 769. So 769 is not close to 650. So the model is not consistent with the data. Good start. Okay, then part 3 asks, what does the model suggest about the number of fruit flies in the long run? So it suggests that their population is just going to keep growing and growing indefinitely. So there is no limit to their growth by the model. Okay, subsequently, it is found that for large values of t, the number of fruit flies in the controlled environment oscillates about 750. So that means the population goes above 750, drops below, above, etc. It's also found that as t increases, these oscillations decrease. So that means when it's been above 750 and then goes below, when it goes back up, it's not as far above 750 as it was. In light of this, Munira suggests a second model. N is 750 minus 250e to the minus 0.092t. Part 4 says to identify 3 ways in which this second model is consistent with the known data. Okay, so N is 750 minus 250 e to the minus 0.092 t. So let's try the initial data. So we know that when t is 0, n is 500. So let's try using the model. Well, we're going to get n is 750 minus 250 e to the power of 0, which does indeed give us 500 as required. Now let's try when t is 10. So when t is 10, n is 650 by the model. N is 750 minus 250 e to the minus 0.92, which gives us 650.4. So that also works. Okay, now for the third one, we need to ask ourselves, what else do we know? We know that the population will oscillate around 750 and the oscillations become smaller and smaller. So that means the population needs to tend to 750. So, let's look at the exponential term. So, as t tends to infinity, e to the minus 0.092t, but because that's a negative power, the value of the whole thing will tend to 0. So that means as t tends to infinity, n tends to 750, because the 250e term is tending to 0. Now that fits with what is known, so there are our three things. Cool. Okay, 5 part A wants us to identify one feature not accounted for by the second model. So we've just said that the E term tends to 0 as t tends to 0. It's never going to be 0, so we are always going to be subtracting a number from 750. So the value given by this model is always going to be below 750. But if we know the population oscillates, then there are going to be times when the population is above 750. So the oscillations are not accounted for by this model. And then the final part wants us to give an example of a mathematical function which needs to be incorporated into the model to account for this feature. So, what functions do we know that oscillate? Trigonometry. So, either sine or cosine. Cool. Okay guys, on that, the paper is done. Good luck in your exams. Really hope you found this useful. Hope to see you around for A level. Take it easy. Take care.